is Antonio DeSimone, and his title is up there. Antonio.
Yes. So as just a few words to test the microphone. Yes, it's working. So as one of the organizers of this workshop, I don't know whether I should thank my fellow organizers for the privilege of addressing you today, but maybe let me take the opportunity to thank the speakers that have come here, that have come before me, because I've really enjoyed immensely what I've seen up to now. So I hope it's going to be at least as enjoyable to you as it has been to me. So I decided to do something a bit difficult, merge my own results with a little preview of what's coming next. Okay? So to give you a little guided tour. So I hope I will manage to do this in time. I will look at the watch, and maybe the chair can signal, yeah, when I'm, yes, so that I stop 5 minutes before, because there is something I want to show you in the last 5 minutes. Okay. So we have had a lot of liquid crystals and a little bit of elastomers. Okay, it has started this morning, maybe a bit yesterday as well. What I'm going to focus in my talk is the coupling between elasticity of a rubbery network and nematic order. Okay, so it's these materials are liquid crystalline systems, so they undergo ordering when the temperature crosses a critical temperature, the isotropic to nematic transition temperature. So there's alignment, there's a nematic director, and the peculiarity of the system is that this takes place in a system in which the polymeric chains to which the nematic mesogens are attached are cross-linked. So it's a solid that undergoes spontaneous deformations, actually I'll call them distortions, when the material goes from the isotropic to the nematic phase. And maybe the cartoon, I'll use my hands a lot. So what happens is that if you have something that is, so the mesogens are attached to a chain, when the mesogens align, they, for example, they may stretch the chain in direction of alignment. Okay? So this happens in a solid, and this is what you saw maybe this morning as well. So you will see a material that is being cycled. So this is low temperature in the nematic state, heated up, it goes back to the isotropic state. And you see a huge change of length, so of the order of 300%. And the cartoon on the right, so the sphere that becomes an ellipsoid, is somehow the conceptual rendering of this distortion that you see physically.
Why is the weight being lifted?
It's to show that it can perform work, but it would work in the same way even without it, maybe with some floppiness, because this is a ribbon. Okay, but it's just to show that it can lift the weight. Okay, now a material like this is obviously very interesting. Okay, so I will work only exploring the coupling between elasticity and nematic director. So there's many other interesting effects, light, electric fields, etc. I will not talk about them. So let me now do the opposite. So we have produced deformations by generating this alignment. Now let's work at a temperature well below the isotropic to nematic transition temperature. So we are in the nematic phase. And now let's probe the opposite. Let's work on the director by applying mechanical loads. Okay? So we have a material that is initially with the director uniformly aligned along the vertical direction in a thin sheet. And we stretch the sheet in the direction perpendicular to the initial director. So this cartoon here is meant to remind you that if the director is vertical, the material likes to be elongated along the direction of the director. Now we pull in the opposite direction. So I won't insult your intelligence. What the material decides to do is to have the nematic rods rotate to adjust the external imposed stretch. And this is this cartoon here. Okay? Now if you look at the signatures of this in the mechanical response, so this is a typical response of a rubber specimen of this kind, which doesn't have these super properties. And this is the way this system would respond, thanks to this internal degree of freedom. Okay? Here is a blow up of this that shows that there's an initial part of standard behavior, so to speak, then a threshold where something interesting is happening. So here there's a knee between two completely different responses. There's a plateau, and then again the standard behavior. Okay, so like in a phase transition, the phase transition is occurring here. It's responsible, so the orientational degree of freedom is responsible for the nonlinearity in the response. Now, this is a liquid crystal, so there's an optical trace of this behavior, and here is the optical trace. If you look at this material, you will see optical patterns, and in fact, it's more interesting than what I was suggesting before, because you see bands. Bands that are alternatively transparent and opaque, signaling the fact that there is a texture, there are bands of director, okay? And so as you will see, this is due to the fact that the rotation of the director is not homogeneous, but it happens in domains, okay? And this is called the stripe domain instability in the literature. Very well. Okay, so crash course on building an energy to describe this behavior, okay? So there are two important ingredients. One is the fact that there are spontaneous distortions, which means modes, I mean, not modes, but states in which the material likes to be, states of minimal stored energy or free energy. Okay, so let's start from this. And this is pretty much entirely contained in the picture that I've already shown. So if we model the system as being incompressible, as it is standard for rubbers, the spontaneous distortion as well will be incompressible. There is a direction of alignment. That's the V direction. It's the only privileged direction. All the directions perpendicular to it are equivalent. There is a stretch in the direction of alignment. So the amount of stretch in the direction of alignment plus the constraint that the determinant of the deformation will be 1 to preserve volume determines everything. And so you know what is the spontaneous deformation. Here is in matrix notation. So here in the background is what I'm going to do. So continuum mechanics, there's a map that tells you the deformed configuration. The key quantity is the deformation gradient. So the ij component is the partial derivative with respect to xj of the ith component of the map. Okay? And there is a special value of that deformation gradient, which is the spontaneous distortion. And here it is. So this is the number. For historical reasons, it's not a, but a to the 1/3. Let me not comment on this. This number bigger than 1, it means elongation along n. These are the two directions. It means this is n tensor n. And this is the stuff that comes from the volume conservation. So all the perpendicular directions to n contract by a number such that the determinant of this should be 1. Okay? In concrete, so in this experiment, this is the deformation. So it's a spontaneous distortion accompanied to the vertical orientation of the director. This is the matrix. This is how much you stretch along the direction of alignment. This is the amount you contract in all other directions. Okay. So this is bit number 1. What is in rubber elasticity is the identity, so to speak. So the material stays there. That's the undistorted configuration. In this system, it's a rich set of energy wealth. It's zero energy states. Now we have to build an energy that tells us how much we pay, what is the elastic cost of deviating from this preferred state of distortion. Okay? So let me borrow an idea from, so here I'm telling you the idea first in nonlinear kinematics and then in linear kinematics. In nonlinear kinematics, the idea is borrowed from plasticity. And when you do plasticity in finite deformations, there is a notion of deformation relative to a preferred state or to a relaxed state. So you have something occurring at the microscopic scale that sets the state in which the material likes to be or goes back when you unload it. And so all the energy, all the elasticity happens in the deformation relative to that state. So in our case, the state, the preferred state, is set by the nematic director. Okay? So we take an arbitrary deformation. Let's focus on the red part here. We take an arbitrary deformation, and there is a nematic director. The nematic director carries a coupling with elasticity. Now, thought experiment, I switch on off a switch, and I turn off the coupling between elasticity and director. So that spontaneous deformation is recovered. And I know what that spontaneous deformation is because I told you yesterday, so I produce this. And so this is the part that is due to the coupling, and the leftover part, this one, is the part that stores elastic energy. Okay? So this is the way of constructing this. So any deformation gets multiplicatively decomposed into a part that is spontaneous and a part that stores elastic energy. And then you extract this part. And here you see the multiplicative structure of nonlinear kinematics, because I want to call this a deformation relative to a certain preferred state, and I don't take the difference between the current state and the preferred state, but I compose with the inverse. Okay? So this is key because of nonlinear elasticity. Okay? Besides that, I go on. I form a standard construct in rubber elasticity, which is the Cauchy-Green strain, and then I take a standard energy from rubber elasticity, which is the Neokian energy, so-called. So it's the trace of this guy here, which has the nice property that it's minimized. So this expression, it's minimized at the value 0 under the constraint that the determinant of the deformation is 1, which is the incompressibility constraint. So this is minimized at the value 0 by this being the identity. Okay? So this is standard Neokian elasticity constructed with an elastic part of the deformation ring. Okay? Very well. And this has the it can be rewritten many other ways, but let me move on. Okay, and this will be our energy. And this has the property, as I was saying, that it's minimized when this object is the identity, which is equivalent to saying this kind of things. It's equivalent to say that the Cauchy-Green strain should be the Cauchy-Green strain constructed on the special distortions induced by n. This is the way of reading this. Okay? I will go back to this after I've done the linear version of this, because the linear version is much more transparent. Okay? Now, what I said, okay, the formula I just wrote down, which I'm repeating here, it's nothing but, after a change of reference configuration, the celebrated formula of Warner and Terentier for the description of liquid crystal, nematic liquid crystal. So it's in the field, it's called the trace formula. And okay, so I was cheating, of course. I mean, I've done a conceptual path to recover that. Okay, let me just make one little observation. So this formula describes a material that, in a sense, is isotropic. The sense in which is isotropic is written here. So you see that the state of spontaneous distortion is a certain function of the director. So if the director is this one, it will be a strain of a to the 1/3 in this direction and a contraction of a to the 1/6 in this direction. Now we do this one. What does the material do? A strain of the same quantity, a to the 1/3 in this direction, a contraction a to the 1/6 in this direction. So there's no difference between this direction and this direction. The material is isotropic. Okay? But I was cycling the temperature before in the movie to show you, to exhibit the spontaneous stretch, and I was saying the material always returns to the vertical direction. So that direction is special. It's not in this energy. We need another energy to incorporate this effect, and we flip in the book, in the magic book, and at some point we find this other energy. So there's a correction to take into account this fact. Okay? So this was the energy that was written before, and now with a beta coefficient that modulates the strength of this correction, I have now appearing a special direction, m0, which in all the rest of the talk would be vertical. Okay? Very well. So this is the background. Now what I want to do is to talk a little bit about work of a former PhD student of mine, who's now in Oxford. So let's do expansion. Okay? So let's do the harmonic approximation of these energies. Okay? What I will do is I will not do any approximation on n. So there will be no small rotations. The rotations will be arbitrary. What I will do is a Taylor expansion at order 2, so the harmonic approximation in terms of the kinematics, in terms of elasticity. Okay? So I do a small strain version of the Warner and Terentier theory with arbitrary large director rotations. So what happens? Let's go fast. So this is the amount of stretch, a to the 1/3. Let's consider that as a small perturbation of 1. And so there's a gamma that appears, which is a small quantity. Okay? And now gamma, like you go from nonlinear elasticity where triviality is 1 to linear elasticity where triviality is 0. So gamma measures the strain of linear elasticity. And so the spontaneous strain. So from now on, I will no longer talk about spontaneous stretch, but spontaneous strain. We can calculate this by expanding this quantity, and what happens is that it's a perturbation of the identity by a tensor, which is a tensor of spontaneous strain. So you will see that something appears here, which is like the Q tensor, the DeSimone order tensor, and this is the spontaneous strain. And now we Taylor expand this energy, and what we get is a beautiful expression, because it's very easy to read. So this is the expression. So it's a constant times a positive constant, the shear modulus, times a quantity which is non-negative, because it's a square, and it's 0 if and only if this is 0. So it's 0 if and only if the strain of linear elasticity, so the symmetric part of the deformation of the displacement gradient, equals the spontaneous strain. So it's very easy to see when this is 0, right? When this equals to that. Okay. This is the geometric structure of the linear theory. Okay. You can do the same thing with the beta perturbation, and what happens is that you get another term with the same structure, but with a beta in front. Okay. And I will discuss this in a second. Now, how does this work? So we've already seen this. So I was telling you that the spirit of the coupling, the key aspect of the coupling between elasticity and nematic direction is that the nematic direction induces, so the nematic phase transformation induces a spontaneous state of distortion, the one the material would like to have, and the energy is the difference of the deformation with respect to that. Before we had to do a complicated construction with composition with inverses. Here you get, as if you were doing plasticity in linear strain, the relative deformation with respect to the preferred one. It's a difference. And the energy is just the modulus of this relative deformation square. Okay? What happens if you do the beta thing? If you want the special direction. So in this theory, this is what happens. And so now you ask yourself whether you can minimize this to 0. And you have the sum of two positive terms. So you can if they are both 0. So this requires that E be simultaneously E0 of n and the E0 of the vertical direction. This can happen if and only if this and this are the same. Okay? So you get a recoil, you get a restoring couple, if you want, or force on the director to the vertical direction through this combination of terms. Is it clear? So this is minimized if and only if this equals that, and this can only occur if this is true and this is true. Okay? Very well. There's one more little step I would like to do. When I talk about the geometric structure of this energy, I want to point out another thing. So I'm exploring only the coupling between director and elasticity. So there's no gradient terms, there's no Frank, there's no nothing. So in some sense, in this theory, the director is sort of slaved. So I'm applying boundary conditions to the displacement, so the director is sort of slaved to the elastic behavior. We are interested in minimizers. We have two variables, the displacements and the director. So maybe we can minimize, when we minimize over two, over two simultaneously, we can do that in sequence, right? So we can first minimize over n, and then over e. So this is a function. These are functions e and n. Now, if we minimize over n this function, we obtain for each, a value for each n, for each e, so a function of e alone. Okay. And so what is this? Is this guy here? It turns out that it's this guy here. And so this is really the distance squared of the deformation gradient of the linear strain from the set of possible states of spontaneous distortion, so the sets of spontaneous strains, right? So there is a set here, the set of spontaneous strain. The energy really is the distance from this set, okay? So there's an orbit that you generate by exploring all the states of spontaneous distortion as n varies, and the energy tells you, okay, the energy is the minimal distance of E from that set, okay? And so let me show you how this landscape looks like. So I want to do this in a simplified setting, so plane strain. So I don't want to follow what happens out of the board, okay? So I will focus only on the plane in the board, so in a 2x2 subset of the matrix. And I use this representation. So I start from the initial state. So in which, in the stretching experiment, we were starting with the director vertically, and we were stretching like this, right? So we start with a material that is prepared so that it's deformed. It's in the zero energy state corresponding to the vertical direction. And then we stretch. Okay? And so this is what I want to do. And I use these parameters, epsilon and delta. And so this is the parameterization I use. Let me show you. Epsilon stands for stretching in the horizontal direction, and delta for shears. Let me follow this. So for example, what happens if epsilon and delta are 0? So there's no perturbation here. So it's the initial state. Okay, so epsilon equals 0, delta equals 0 is the initial state, this one. So the material is like that. Now what happens if, for example, delta equals 0 and epsilon is 1? So I do it here, and you see that this has the effect of exchanging the role of these two. Nothing changes here. So 1 changes this to 2/3 and this to -1/3. Okay, so when I've done this, so this state here corresponds to the states of preferred deformation when the director is horizontal. Okay, and then as epsilon and delta vary, I get all the zoo of possible deformation. Okay, so these are two special states, and I ask you to remember these because I will point them out in the energy landscape. Here is the energy landscape. So now I'm plotting the energy as a function of epsilon, the amount of horizontal stretch I'm imposing, and delta, which has the meaning of the shear the system experiences, either in this direction or in this direction. Linear elasticity does not, the symmetric tensor E does not distinguish these two. Okay? And so this is the initial state, 0, 0. Okay? And the energy is 0 in the initial state. Then what I'm plotting are the level curves of the function I've written down. So it's written down. You put it in, this is MATLAB, okay? You put it in MATLAB, you get the level curves. And here are the level curves. So there's a 0 level curve, which is the circle, the green circle. Then the energy, let's follow a cut here. So I'm following the behavior of the energy when I'm stretching the system to half the amount it would like to be stretched to have horizontal director. Okay? So this is the section, and I see high values at plus 1.5. So then I go down, I get the 0 here. Then I go up here. Then I go down here. Then I go up. Okay? Very well. The circle is not by chance. I told you that the geometric structure of the energy is really the fact that it's the distance from an orbit which represents the state of spontaneous strains. And here we see it. The energy is precisely the distance from the circle. What else do we see? We see that it's non-convex. Okay? It's definitely non-convex. Now, here it's the only place where it's singular. Okay? If I did a cut just before here, I would have seen something smooth. So I would have seen something, smooth here, okay? So let's think of this instead of that, so that it's easier. So what else does this plot tell us? Well, imagine we do the experiment. We stretch, okay? And we stretch, and we want to, and we stretch, and we don't do any shear, okay? So we have a sample, we stretch it, and let's test the unsheared state. Okay, so I want to test epsilon from 0 to 1 and delta equals 0. Okay, so what I have to do, I have to start here. I have to move along this line. And this is the energy. Okay, if the material was uniformly deformed according to the boundary conditions I'm applying, this is what the energy that we would see. Okay? And now here, we have material where if we take the second derivative of the energy with respect to delta, with respect to the shear, what do we get? Two derivatives of the energy is the shear modulus. Okay? So if we calculate the material, the shear modulus of the material at this point, and we do little perturbations up and down, we are probing the curvature here. The curvature is negative. The response of the material is unstable. The material is unstable towards the formation of shear bands. The shear modulus is negative. And we have somehow the whole plot of the energy, not only for small perturbations, but only very far away. And so we see that if the material shears a lot in the positive and negative direction, it can even reach a state of zero energy. Okay? So this is the stripe domain instability. The material is unstable in the unsheared state. It develops two shears, plus a certain quantity, minus a certain quantity. And in this way, it manages to produce a globally unsheared deformation. Okay? Let me show you this. This is the idea. You replace a high energy state with two zero energy states, which correspond to two equal and opposite shears. And in this way, you achieve zero energy. So a macroscopic unsheared state can be realized with a fine system of shear bands, okay, that can be made as close as you want to the imposed condition, because here you see the mismatch. But if I make this layer smaller and smaller, the mismatch will be smaller and smaller. And so provided there's enough separation of length scales between your scale of observation, the macroscopic sample, and the scale of the response to the material, the shear bands, you get zero energy for the state you are prescribing. Okay? So this is the way the material accomplishes, this ideal material accomplishes zero energy state. And I can repeat the calculation for any point here. Any point here can be obtained as the convex combination of these two. Okay? So I replace the central portion of this Mexican hat with the chopped Mexican hat. Okay? I convexify the energy landscape. And in fact, I'm oversimplifying things a little bit, because in this representation, it is a convex envelope. But I must, in fact, point out that it's a bit more complicated than what you're used to, for example, when thinking about Maxwell lines or van der Waals coexistence of phases. So I'm doing a convex envelope, but I'm doing a special convex envelope by using, say, I'm mixing not densities, not scalars, but deformation gradients. Okay? And for this to be legitimate, there is an integrability condition, which it's called kinematic compatibility. So my construction will be legal if and only if I can exhibit a y, a deformation, whose gradient is the construction I'm doing. So here it is like that, because I'm using only shears. Okay? And the compatibility across these interfaces is guaranteed by construction. In general, if I do complicated construction, I have to guarantee that the construction works, and it can be generated as the gradient of a deformation. This is why this is not called the convex envelope, but it's called the quasi-convex envelope, because it's the convex envelope subject to kinematic compatibility constraint. Okay? No. The answer is no. There's no simple criterion. In fact, yeah, maybe I will point out the expert in the audience later with whom you should discuss this. Okay. But there's no general criterion for this. And in fact, in some sense, so this is, so this is a case, I mean, so, no, it will take me too much time. So in this case, you get by with the convex envelope in the sense that you construct it. I mean, it comes out of a construction, and so the construction gives you somehow an upper bound for the, so you have exhibited a low energy construction, and maybe there could be something that beats that, and what you have to prove is that there is nothing that beats that, okay? But this is a very wide and open area of mathematics, I would say. Let me first say how to use this. So we have constructed, effectively, somehow a renormalized energy landscape in which, to each state of putative imposed macroscopic deformation, we compute the minimal energy cost the system can achieve compatibly with that microscopic deformation by developing microstructures. Okay? And now we can do the experiment. So I can stretch. I can forget about whether there is or no microstructure. I just use the renormalized energy. And what I have to do is I go from energy to stress by taking one derivative. Right? So if I have the energy landscape, I get the stress-strain response by taking one derivative. And here we start from here, no stress, and then stress. Okay? So here is the response we get. Blah, blah. Here you can see the remnant of the the fossil, actually, of the Maxwell equal area construction. So we can do any response. This is this one. Let me show you what happens, how the picture is perturbed if you add the beta perturbation. The beta perturbation is a very nice perturbation. It's convex. It's exactly the same, except that there's no set. So this one is the distance from a set. The beta perturbation is a quadratic term that tells you the distance from a point. It's just a quadratic perturbation of this, and it makes things nicer. So near the initial state, so I'm adding a parabola to this energy landscape. So near the initial state, which is this one, the energy looks pretty much like the standard elasticity energy. Now, when you drive the system away from this state, the non-convex part shows up, and there's a similar construction, except that it's shifted. Okay, so you can work it out, but the ideas are exactly the same, and this produces the response you want to see, which is initial hard response, plateau, etc. Okay, so this is somehow the way the system responds. Very well. I look at the clock. So what I told you about is the plane strain construction when everything can be done essentially on the board, okay, if you have the right viewpoint. The 3D version of this is a bit more complicated. I don't want to discuss it in detail, just two things. So I have to use more coordinates. I have to use other things. So this is the energy landscape. The only thing I want to point out is the following, that so let me look at this. These are certain coordinates. This is the original energy landscape. And what the convexification construction does is to, one of the things it does is in a certain portion of this diagram, it replaces, so this is the initial state of the system. So in a certain portion of this diagram, it replaces these curves with 0. Okay, so this is this green stuff. So the construction says that there's a whole open set of deformations that cost 0 energy. Okay, this is the ideally soft response of the system. Now I want to focus attention on one point. This one, 0, 0, which in the nonlinear case is this one, 1, 1. Okay? So why am I doing that? Because in order to get that point of the diagram, you need to use more complicated constructions than the one I was using. So I was using layers, which are here. And what we have to use is layers within layers, or rank 2 laminates, or whatever. So this is the pictogram of that. So systems of layers that meet. Okay? Now, it's interesting that in order to reach this point, you have to use this type of construction. Why am I raising this point? Because you have a system in which the spontaneous distortion consists of a stretch in one direction and a contraction in the other one. So it's a uniaxial deformation. This is the state in which you bring the system if you compress this a bit and enlarge that a bit. So it's a state which is biaxial. Okay? So it's a state which is very far away from the states of spontaneous distortion. And in fact, you see it here. It's very deep, buried in this green sea. Okay? Let me read this deformation in another way. So what is the 0, 0 or the 1, 1? So I'm using as reference configuration the undistorted configuration of the high symmetry isotropic phase. So this is the state that the system would have if it was in the high symmetry isotropic phase. Okay? So in computing this energy, I'm asking in a different way the following question. Imagine I have a little ball of this nematic elastomer, and I bury it into steel. And steel does not deform. And now I am at high temperature, above the isotropic to nematic transition temperature, and now I undergo this transition. Okay? So I impose, with the boundary conditions, no deformation. 0 or identity, depending if I'm doing linear or nonlinear. And I'm asking myself, what is the energetic cost of the minimal energy deformation the system can develop inside this cage of steel? The answer is 0. Okay? So in martensites, this is called the self-accommodation property. It's the fact that you can develop a plate of martensite in a rigid matrix without storing energy. Okay? Here, it's the fact that You can achieve this complicated biaxial state of deformation if you want with respect to the axial phase if you do this type of things, okay? This will come in a minute or so. Very well. Now, I talked a little bit about quasi-convexity. Maybe I should point out that it's an important topic in the calculus of variation. There's lots of questions that relate this question to the question of the existence of minimizers of variational problems. There's a lot of interesting literature of applications of these ideas here in the context of liquid crystal elastomers, but I want to go fast. So I skip completely the application of this, the glorious application of these ideas to predict experiments. Let me just move to something that is even more satisfactory, which is the fact that these ideas, and in particular, the story of the self-accommodation of Martensite that I was mentioning before. So the fact that you can accommodate the state in which the material likes to be at high temperature with zero energy. So it has found applications in a wide field, I mean, a very interesting field in pneumatic elastomers. So the response of polydomain sample started with the seminal work of Uchida. We'll get talks by Kenji Urayama and a talk by John Biggins. And this idea is instrumental in somehow rationalizing what's happening in the behavior of these materials. So in producing somehow this theoretical curve. Okay, so we will see this later on in the program. I've been talking mostly about the energy landscape, so the global structure of the energy. Of course, shear moduli are very important. I've used it to motivate the instability of the unsheared state. And okay, it's a very rich topic. It brings us back to the origin of this field. So DeSimone that somehow proposed the coupling, proposed somehow with a calculation, somehow the fact that there should be an interesting material behaving like that. The early stages of thinking about vanishing of shear moduli as a consequence of a continuous broken symmetry, Tom Lubensky. And there's experimental verification. Marty will forgive me if I'm slightly distorting this idea, but there's experimental verification of the fact that when you drive the system deeply in the nonlinear regime by stretching, you can get the shear moduli decreasing and maybe vanishing. Okay? And this resonates a lot with what Vincenzo Vitelli was saying this morning, but hopefully this will be an excuse for him to join us in the next few days, and there will be many more talks about this. Okay, 5 minutes. I want to close with one obvious idea. So polydomains is a very important topic. It's a very interesting topic, and we will hear a lot about it. Another very important topic is, we've had one talk already about this, is active shape control. So these are active materials. These are materials that change shape in response to a stimulus. And so it's obvious that you want to use them to achieve changes of shape, to do interesting things. And it's obvious that you want to ask the question of what you have to do to this material, how you have to engineer this material in order to produce a desired shape change, okay? So there will be many talks about this. I will not spend time, but we have had one. There will be many more. Let me just show you one example, which is the most exciting for me because it's the last one that came from our group. And the connection with liquid crystal will appear in a couple of slides. For the time being, this is a unicellular organism. Okay? So this is an euglena. It's something that swims in fresh waters, and you are seeing it moving. Okay? Very well. Now you see it moving, and you say, how does it move? And you see it here, and now you start thinking, well, maybe I put fibers. Maybe, I don't know, I shine light. Maybe, who knows, right? Now, in these things, it's still true, I think, that at this scale, which is a few microns, or maybe tens of microns, nature beats engineering. And so it's worth to have a closer look, okay? So this is, we have looked at this, we covered, digitized the movement, et cetera, and we also started to do the simulation of the flow, right? So this is in a flow, this is swimming. And so you put this in a solver, and you solve for the fluid flow with the non-slip boundary condition, okay? But at some point, you get another micrograph, okay? Now, this is this, okay? So if you look at it at smaller scale, this is SEM, this is optical microscopy, you see that these things have these interesting strips. And in fact, it's known that in order for the system, for these bees to produce this type of behavior, there must be many. So this doesn't have this type of motion, this does. Okay? So then you start thinking some more, and you get sort of excited about this. And you say, well, here the stripes are almost vertical, and the thing is thin. Here the stripes are almost horizontal, and the thing is fat. Maybe stripes and shape are related. And then you say, well, maybe there are strips. In fact, this is true. There are microtubules underneath, that manages to slide one strip next to each other. And maybe you say, this deformation is produced by the relative sliding of the strips. And then you test this idea. You see whether it's possible that a wave of shear deformation traveling along the system, like I'm having here. So this is unsheared and this is sheared. Here there is a band. Here is time, and here is a coordinate along the system. I have a traveling wave of shear. This produces a traveling bulge in the system. You put it in your solver, you compute the motion, and this is what you get. So these are systems that, on which there has been a reconstruction of this hypothetical motion, and they are swimming in the way that they would swim in a fluid by solving the Stokes equations outside with a non-slip boundary condition. Okay? So there's a whole range of speed that you can accomplish depending on the type of actuation that you use. Okay? There's a faster, there's a smaller, etc. Very well. So what has this to do with elastomers? Okay? Not very much, but hold on. First of all, how does this work? So the easiest way I have to show you is the following. So I say that I can produce expansion and lengthening and shortening through sliding of strips. So let's do it like this. I have a cylinder. I cut it. I open it. I imagine that there's no bending deformation, no bending energy, so this is free. Now I shear it. So this is the shear. I shear the pellicles, one with respect to the other. Now I rotate it, zero energy. Now I refold it, zero energy again because there's no bending. This is a shorter and thicker cylinder. If you want to see the practical realization of this, it's in my office M3 at the Newton Institute. Here it is. And how does the euglonid work according to us? And here's the connection with the liquid crystals. So it works by localizing this. Okay? So if you localize this mechanism, and okay, you have to ask yourself, can I? Okay, but let's assume you can. Then you localize it, you drive maybe a light source along here, and you get a propagating bulge. Okay? So in some sense, there is a material that would behave like this. It's a smectic C elastomer. So if we could make a smectic C elastomer like this and shine a light, this would be exactly the behavior. James Adams will be talking about smectic C elastomers. Thank you very much. And I've been asked to put this up. There's a conference on liquid crystal elastomers that will take place in Shanghai. The chief organizer is in the audience. He will give a talk. Thank you very much.
Thank you, Antonio. Antonio squeezed into his question time,
I know.
the last topic. So I think in fairness to the next week, we should probably proceed. But thank you very much indeed. A wonderful talk and on many areas very close to our hearts. So let us thank once again.